I'm Hasra, and I'm a PhD student from University of Edinburgh School of Informatics. So today I'm going to talk about my work with my supervisor Mohan Sridharan. So about an architecture ad hoc teamwork which combines knowledge-based reasoning with interactive learning. So when talking about ad hoc teamwork, we basically talk about collaboration of agents without prior coordination. So for example, here you can see the two domains. The first one is fort attack, where you have a team of guards trying to protect a fort from a team of attackers. And the second one is a soccer domain. So you have a team of offense players trying to score a goal against a team of defense players. So the idea behind these teams and work is that the agents, they have limited prior knowledge of each other. They can have different representations and may have no experience working as a team before. And the domains, they can contain a lot of uncertainty. They can be fully or partially observable with or without restricted communication. So this is actually representative of many practical applications in robotics, like disaster rescue, space exploration, where you want robots and humans to work together, although they may have no experience working as a team before. So the agents, they have to learn interactively from whatever they observe, try to understand the behavior of each other, and come up with their own actions so that they can achieve the team goal. So ad hoc teamwork is actually a well-established research area and has been around for at least 15 years. And the earliest approaches, they used to have these encoded protocols or plays to select the actions of the ad hoc agent based on different states it observes. And then it transitioned from there to something having main two components. That is, the first component is to estimate the behavior of the other agents in the domain. This is usually based on probabilistic or deep neural network models. And then it tried to optimize the actions of the ad hoc agent based on a long history of experiences. So since these methods are mainly focused on the data-driven approaches, they are usually prone to limitations like being computationally expensive and being able to, or actually being hard to utilize the common sense domain knowledge available in many of these practical applications. So which makes it hard to adapt for these agents to different uncertain situations that they have to face in these domains. And also they actually lack the transparency that can be, that is actually desired from such systems. So in this work, our takeaway was that instead of just looking at this as a data learning problem, try to combine the knowledge-based reasoning with it so that they both can address each other's limitations. So our inspiration lies in cognitive systems, which are in turn inspired by human cognition and control. So we have different components for representation, reasoning, learning, and acting, and they have different abstractions, but we have a knowledge transfer which make them couple together. And then to provide the transparency, we want the agent to be able to provide relational descriptions of its decisions and beliefs. And then we also want the agent to be able to interactively learn and revise previously unknown axioms. So it can learn new things, merge those axioms to add its existing knowledge base. So I'll give a brief look at the architecture. So basically, if we take the fort attack domain, so the environment is going to be your fort and the surrounding, and the agents are going to be your teammates and opponents. So if the guard agent is the ad hoc agent, then your teammates are going to be the other guards, and the opponents are going to be the attackers. So these agents, they are going to receive the state observations and execute their own actions in the domain. And the ad hoc agent is going to have two main components. The first component is based on the learning. So this is used to create the predictive models of the other agents. So these are done based on the state observations it receives from the environment. And the next component is the knowledge representation and reasoning component, which has the declarative knowledge and the reasoning component. So to do this, the agent again uses the state observations from the environment and the action predictions from the learning component. So based on these components, it will select the actions and they can be executed on the environment. So continuously, this cycle is going to be there, and the agent can use the new state observations to revise the models when needed. And then we have the explanation generator component, which consists of the analyze and text converter. So again, the agent is going to use the predictions from the learning component and the current knowledge base to generate the explanations. So when you ask a query, it's going to be converted from the text converter to something that the agent can understand. And inside the analyzer, the agent will decide what made the agent to have this particular belief or do that particular action. And then again, those literals or the things that selected will be sent back to the text converter to create the explanation that can be understood by the human or another agent. And any new observations or new data that is learned in this experience can be used to actually modify the component, the predictive models that you have. And the final component is the axiom learning component, which is based on decision tree induction. So you use the existing knowledge base, and any new learned axioms are again merged to the current knowledge base. So this is the overview. I will try to give a brief idea on what is inside each of these components. So the first component is the knowledge representation and reasoning component. So here we use action languages to describe the common sense knowledge of the agent. So it has a system description, which consists of a signature and a set of axioms. So the signature looks like things like the relations about the particular arrangement of places in the domain, the location of the agent at a particular time, and the actions the agent can execute. And then it's going to have different type of axioms. So here I have set of axioms to get an idea. So the first one says that moving to a particular location causes that the agent to be in that location. And we can also specify axioms like the agent cannot face two directions at the same time when you are trying to rotate. And then we can also try to have axioms like to prevent the agent from trying to take a shooting action when it doesn't have any other attack agents in its shooting range. So apart from these axioms, it also has a partial history, which consists of prior observation and action execution of the agent, and also some initial state defaults. So based on this knowledge, the agent can do planning tasks, diagnostic tasks, and to do this is use answer set prologue. So doing answer set prologue here is important because it supports non-monotonic logic, which is the ability to revise the previously held conclusions that the agent is having, which is important in these kind of uncertain domains. And then another important aspect of the architecture is the use of refinement. So here the agent can reason in two resolutions at each time. So for example, in the photo attack domain, if the agent wants to shoot an attacker, then it needs to know exactly where the attack agent is in so the shot can be successful. So in this case, it needs to reason in the fine resolution. But if it only need to know a general idea of the location of the agent, then it can do it in the coarser resolution. So at each step, the agent can decide whether it want to reason in the coarser resolution or it need to zoom into the finer resolution. This is important because this allow this system to be scalable to much larger and complex domains with much larger sizes and as well as much and very high number of agents. And then, so having only this knowledge is actually not enough in ad hoc teamwork because the domain itself and the agents are going to be changing over time. So you want to have the predictive behavior models of the other agents. To do this, we follow the ecological rationality approach. So ecological rationality actually talk about adaptive satisficing, where you characterize the behavior as a function of both cognition and the environment. So we use the algorithmic model of heuristics so that we can ignore part of the information to make the decisions more quickly and accurately, because that is important in ad hoc teamwork. So by doing this, we have selected to learn an ensemble of fast and frugal trees. Here you can see one of the trees that we learned for a guard type agent. And as you can see, they are very sparse models. They have limited spread and depth and actually easy to interpret by the humans themselves. So then we come to the results. So we evaluated the architecture in two domains. The two domains I showed before, the fort attack and half-field offense. So here you can see the accuracy of the models, the predictive behavior models that we learned for the agents in these domains. And one of the things that we are trying to do is to learn these models with limited examples. And we could see that by using the predictive behavior models as the fast and frugal trees, we can actually do that with much less data than what is used by the state of the art. So for example, in the photo tag domain, we only use 10,000 data, while the state of the art methods, they try to use millions of data. So the accuracy is not very high. It ranges from 60 to 86. But still, when you combine it together with the reasoning, they can perform better than what is existing. So then, another important aspect is you being able to adapt to the new teammates and opponents and scenes that you have not seen before. So to do this, we train the agent with simple hand-coded policies, which does not have any complex behaviors. And we tested it with some sophisticated built-in policies, which are based on graph neural networks. And the agent has not seen them before at all. So we could see that incrementally, the agent can learn new models, select the existing models, revise them, so that it can adapt to these teammates and opponents on the fly. And it can do it much less data. And overall, it can perform better or comparable with the existing state-of-the-art methods, which are again only based on deep neural networks and things. And also, it can perform better than agents, just only use the knowledge-based component of the system. So I think this actually emphasized the importance of combining both together. And this is actually an interesting example that we saw when we are doing the experiments. So agent 7 here is an ad hoc agent who's following the combined architecture. You can see how well it actually cooperates with the other agents, how it positions itself, and even though they lose one of their teammate unexpectedly in the middle of the game. So what we did was we tried to remove some of the agents in the middle of the game. We let them do some behaviors that the agent doesn't expect, and we try to see how well it can actually adapt to these kind of situations. So actually we were able to see that it can even shoot goals even in this kind of very tricky situations. And then when come to axiom learning, what we try to do is we try the agent to make learn previously unknown axioms. And to do this, we use decision tree induction. So here you can see part of the tree that is learned by the agent to learn this axiom, which says that the agent cannot shoot if it doesn't have the control of the ball in a soccer domain. So here you can see the precision and recall values, which are actually good. And this is not just for learning the single axiom, but it's for learning multiple axioms at the same time. And here we have the performance when it does this in the domain. So you can see with the agent actually can perform better when it has these axioms other than not having these axioms in the domain. So finally, to provide the transparency, instead of actually trying to describe all the decisions made by the system or trying to make the whole model interpretable, what we tried was make the agent to explain or provide explanations to different questions on demand. So the agent can actually answer to several types of questions at the moment. So here I have several examples. The first one is where it can answer to questions like why it decided to select particular type of actions. And then it can also answer you when you ask questions about why it did not select some particular actions. Another thing is that it can justify the beliefs that it's having. So you can keep on asking questions and you can go much into details in these sections. And also you can ask questions about the agent about the actions of the other agents in the domain. So to do this, it uses the transparent or the decision tree transparency so that it can provide answers about the other agents' actions. So to conclude, the contribution of this work was that an architecture that used non-monotonic logical reasoning, probabilistic reasoning, and interactive learning, where they inform and guide each other. And we have a clear separation of concerns. So this is not just the methodology for these specific domains, but it can be easily applicable to other domains. And we use stepwise refinement, which allow the architecture to be much scalable to much larger domains. And also we use ecological rationality for reliable and efficient reasoning and learning. And the agent is able to provide interactive explanations of decisions constructed on demand. And finally, the agent can learn previously unknown causal laws and executivity conditions. Thank you.